Hello, this is Hideo Kobayashi. From now, I'm going to start Kobayashi YouTube University of Science and Technology. Okay, let's move on to today's slide. Okay, let's get started. Kobayashi YouTube University of Science and Technology. The 13th delivery. And today's topic is Modern Control Theory, number 1. Control input that minimizes evaluation function. So today, I'm going to talk about, explain about the important point, one of the important points, most important points of modern control theory. Especially for evaluation function. So as for PID control, I already explained about PID control. These are also called classical control. And that control theory, we didn't use evaluation function. But here we newly introduce evaluation function for modern control theory. But this is sometimes difficult to understand as for the meaning and also the equation. Okay, let me introduce myself. I'm Hideo Kobayashi. I am part-time lecturer at Graduate School of Nagoya University. I also run my company named ITO, which is a technology consulting company. According to the customers' technical requests, I go to every company, not only in Japan, but also the world. Okay, this broadcasting is from Odawara City, Kana Prefecture, Japan, to the world. Okay, let's move on to the next slide. The evaluation function in modern control theory. This function, evaluation function, is usually expressed as J. We use J. J equals this integration. So from the beginning, it's very difficult to understand the meaning of this integration. But without understanding of this integration, we cannot know the meaning of evaluation function. Okay. So integration means usually sum. Okay. And here, this one, first term in parentheses, and this one and this one. This one, x, okay, where xt, state variables. In modern control theory, it's complicated. So, to make clear between each situation and the control systems, we use state variables. State variables. Okay. So this, for example, means, for example, xt means distance, for example, of the movement of the moving body. UT, state feedback input, feedback. So here feedback is given to the system. In that case, considering feedback, then we think about state feedback input. State feedback input means is given to state variables, okay? Q is weight matrix, R is weight scalar, sometimes weight matrix. But in this case, I give this R as a scalar, okay? For simplification. Okay. Then here, this xt is state variables. This means this t means transpose times q times xt. Q is usually coefficient, which is expressed by matrix, but coefficient, weight coefficient usually. So as for the dimension of this term, x times x, okay? X, suppose this x is distance, this also distance squared. If the distance is measured by the sensor using electricity, voltage, in this case, this times this one becomes voltage squared. Voltage squared means in electricity, it's electrical power. It means electrical power. So this means the behavior, moving behavior of the object is expressed by the moving energy, electrical energy. We can think so. And R times ut squared. R is also a weight scalar. So no dimension. This doesn't have dimensions. This Q also doesn't have dimensions. UT input is given to the system as voltage. So this is also becomes a voltage squared, means electrical energy, electrical power. Okay. And this is state feedback input. Input is given to control the moving object. Okay. So this is the situation's movement, this first term. The second term is to control this first term situation. Input, UT, is given to control the movement of this one. Okay? And this is the contents of the J, which means evaluation function. Okay? So in accordance with the value, magnitude of this UT, this value, I mean the first term, changes with UT. Okay? So to minimize J, the control is made. So this control system is called optimal regulator. Optimal regulator. Okay. This optimal regulator is one of the biggest results in modern control theory and the development stage of the modern control theory historically. Okay. To obtain the feedback input. So this is important. Depending on the state feedback input, the behavior of the moving body changes. The Riccati algebraic equation is used. This one. The equation 2 is called a Riccati algebraic equation. Okay. So this is very difficult. So in the engineering side, we use this Riccati equation from the math field. Just we apply this equation to the modern control theory. Here, in that standpoint, I use this algebraic equation. Okay. So here, A is given. A is given. Okay. From the state equations, A is given. R and Q are also given by the designer of the controller of the system. D is also given in the state equations. So the unknown is just P. This is from. Sorry, I made a mistake in writing here, which is obtained from this formula. It's substituted to the formula 3. So P is substituted to formula 3 here. Okay, then UT is obtained. This minimizes the evaluation function J written above. Okay. To make the evaluation function J minimum, P obtained from this Riccati equation is used. Then by this right side calculation, the left side UT is obtained. This is a rough theory about the point in the theory. Okay, thank you very much for today.